Physics Explainer. Today, we're going to uncover the hidden cosmic rules that govern everything, from the tiny twitch of a compass needle right up to the raw, explosive power of a lightning bolt. I mean, have you ever actually stopped to wonder what invisible force physically connects everyday objects, like that simple compass, to the massive electrical discharges high up in our atmosphere? They totally seem like they belong to completely different worlds, right? But as it turns out, they are ruled by the exact same physical laws. So, here's our roadmap for today. 1. The electromagnetic connection. 2. Meet the Lorentz force. 3. Force on a conductor. 4. Motion in magnetic fields. And 5. Calculating the magnetic field. Let's jump right in. Section 1. The electromagnetic connection. A connection discovered. We're going to start this whole detective story with a completely serendipitous scientific aha moment from the summer of 1820 that literally changed our understanding of the universe forever. So picture this. During our routine lecture demonstration, a Danish physicist named Hans Christian Ørsted accidentally noticed something weird. He saw that an electric current running through a straight wire caused a nearby magnetic compass needle to physically deflect. Which is wild because before this exact moment, electricity and magnetism were thought to be completely unrelated phenomena. To figure out what was going on, Ørsted mapped out these invisible forces using iron filings, and he conclusively proved that moving charges, or currents, directly produce a magnetic field in the empty space around them. He noticed the compass needle always aligned tangentially to these invisible circles. Plus, he realized that if you crank up the current, or just get the compass closer to the wire, the magnetic effect gets significantly stronger. Section 2. Meet the Lorentz force. Rules for charges. Now, fast forward a few decades. Scientists really needed to understand exactly how this newly discovered invisible magnetic field interacts with other moving charges. Enter Hendrik Antoon Lorentz. He built upon a ton of extensive experiments from his peers to give us the strict mathematical rules for how tiny charged particles behave the second they enter these magnetic fields. Basically, he gave us the formula that bridges the gap between the invisible field and the actual physical push that a particle feels. Now, the Lorentz force has some highly specific rules. The biggest one, it only acts on charges that are actively moving. If a particle is just sitting there doing nothing, the magnetic field completely ignores it. Also, the force entirely vanishes if the particle happens to move perfectly parallel to the field lines. But when it does act, it pushes completely perpendicular to both the particle's direction of travel and the magnetic field itself. Oh, and keep in mind, a negative charge feels a force exactly opposite to a positive one. A great way to visualize this perpendicular force right now is by using the right-hand rule. Seriously, try it. Point your flat fingers in the direction of the particle's velocity, bend those fingers toward the magnetic field lines, and then extend your thumb. Your thumb is now revealing the exact direction of the resulting force on a positive charge. It's honestly like a brilliant little physical cheat code to help us understand a super complex invisible force. This actually brings up a really crucial comparison that is essential to grasp. See, while an electric field can physically do work and change a particle's speed by pushing it from behind or pulling it forward, a magnetic field does absolutely zero work. Because it always acts perpendicularly to the motion, it essentially just acts as a steering wheel. It changes the particle's direction without ever speeding it up or slowing it down. Section 3. Force on a conductor. Macro-level forces. All right, let's scale this microscopic concept up a bit. We're going from a single tiny moving electron to an entire physical object you could actually hold in your hand, like a current-carrying wire. Think of a wire like a microscopic highway where millions of charged particles are all moving together at once. By grouping all those single Lorentz forces together, we find that we can calculate the total macro-level magnetic force just by combining the current, the wire's length, and the external magnetic field. Because of that perpendicular geometry we just learned from the right-hand rule, all those millions of tiny pushes perfectly combine into one massive total force on a macro scale. Section 4. Motion in magnetic fields, geometric trajectories. So, because magnetic fields only change a particle's direction and not its actual speed, they force these particles into some truly fascinating, dance-like geometric trajectories. For example, when a charged particle's velocity is perfectly perpendicular to the magnetic field, the Lorentz force acts exactly like a centripetal force. By constantly steering the particle inward, perpendicular to its path, it locks the particle into a continuous, perfect circular orbit. It's exactly like swinging a ball on a string around a central pole. But if the particle doesn't enter perfectly perpendicular, and instead has some forward velocity running parallel to the field, things get even cooler. That forward motion continues completely unaffected because remember, magnetic fields don't push parallel to themselves, while the perpendicular motion spins the particle. This combination creates a beautiful corkscrew, or helical shape, and we actually measure this by its pitch, which is just the exact forward linear distance it covers in a single spin. Section 5. Calculating the magnetic field, creating the field. Up to this point, we've focused on how magnetic fields affect moving charges. But to complete our whole narrative loop here, we finally have to reveal the exact math behind how moving charges actually create these magnetic fields in the first place. So, enter the Biot-Savart law. This is a brilliantly elegant mathematical tool that perfectly models how even a microscopic, infinitesimal piece of current-carrying wire generates a magnetic field at a specific point in space. It also proves that the magnetic field falls off with the square of the distance, which is just like gravity. This creates a really fascinating contrast with static electricity. Unlike Coulomb's law for static charges, which acts as a simple scalar source pushing out a field in a straight line, the Biot-Savart law dictates that a magnetic field relies on a directional vector source. The current literally has a direction, and the resulting field always projects completely perpendicularly to the plane containing the current and the distance to the point of interest. Now, as we analyze the exact mathematical constants used in these equations, specifically the permittivity of free space used in electric fields and the permeability of free space used in the Biot-Savart law, we kind of stumble upon one of the greatest hidden Easter eggs in all of physics. It turns out when you combine the absolute vacuum constants of static electricity and magnetism, they perfectly and magically equal the exact speed of light. This incredibly simple mathematical relationship proved, once and for all, that light itself is just an electromagnetic wave, meaning everything we've talked about today is part of the exact same cosmic fabric. So if the very speed of light in our universe is really just a byproduct of moving charges and magnetic fields interacting, it definitely leaves us wondering what other profound, invisible cosmic rules are silently shaping the reality you're experiencing right now. Keep asking questions, keep looking at the world through the lens of science, and thanks so much for joining me in this explainer.